In fact, there is also a prime-based number theory called totient calculus, developed in the 1930s by, among others, Katz and Paul Erdos.
Is there any connection between prime numbers and probability numbers? Prime numbers are comparable to irrational numbers, because both are such that an individual number cannot be calculated by any formula. However, what about the concept of real numbers? Here an intriguing observation is revealed. Even numbers that end in 0, and numbers that are divisible by 5 are never prime numbers. Numbers can be prime numbers, but they are not always. This offers a chance for comparison. But how to compare primes to our prob sequence? Compare prime nums to other probs? Compare prime and comp nums to other probs? Compare prime nums to other trays? Prime nums have 1 char, end in 4 nums? 1, 3, 5, or 7. This could be the foundation for initiating a comparison with probability numbers.
To clarify, it is important to note that if a number ends in 1, 3, 7, or 9, it does not automatically imply that it is a prime number. The presence of these digits at the end does not necessarily indicate its status as a prime. However, if the number does not end in 1, 3, 7, or 9, it is definitely not a prime number. So it is advantageous to examine precisely these 4 types of numbers. These can be examined, for instance, by creating a coordinate system and cardinal directions for analysis. For example, if the number is 1, we draw a line from a point in an upward direction to visually represent the value of 1. The following number is, let's assume 7, we make a move to the left, and then the number is 3, we move it to the right once again, and so on, continuing this pattern of alternating left and right movements as we progress through the sequence of numbers. So in 4 directions, this line moves in various directions, and gradually, as it is followed, it leads to new discoveries.
Hence, when generating prime numbers, we examine the scenario where the last digit is 1 in order to obtain the desired outcomes. When examining prime numbers, it is advisable to look at the last digit when it is 1, 3, 7, or 9. Following that, proceed to compare this series to prime numbers using a similar approach or method of analysis. This can be achieved, graphically, in the subsequent manner.
Prime numbers, irrational numbers, and random numbers all have one common feature in common, which they share. They are unpredictable and hence fascinating to compare. Now, I have compared prime numbers to random numbers in a way that, of course, does not reveal anything about prime numbers or predictability, but it does reveal something about them and adds to our understanding of their nature. It seems that they are not very random, and what does that even mean? I wonder about the lack of randomness. Here's a curve I created using a computer a while ago. It was made on an old school machine, so I need to redraw it from the screen since I don't have the original file. The machine ran that graph for 3 days, and this kind of result came out. Prime numbers came out, or random numbers came out completely different and much broader in appearance. However, this is the type of matter that, in my view, would necessitate further investigation.
However, why would prime numbers actually be of such great significance? Let's examine these operations more closely. As an illustration, moreover, it is important to note that not all numbers are, in reality, prime numbers in addition to the aforementioned points. In spite of the fact that 3 is the sum of 1 and 2 or the sum of 1 and 1 and 1. If we go beyond multiplication and consider the concept of powers, so a corresponding reference point could be, for example, 2 to the power of 2, which is 4, and 3 to the power of 3, which is 9. During the intervening period, there are a significant number of numerical values that exhibit similarities to prime numbers in terms of their properties and characteristics. Let's consider the next hyperoperation, which is the power of the next level. That is 2 raised to the power of 2 raised to the power of 2. The total count of 2's is 3. This calculation yields a total of 64. We can proceed a bit further to continue our analysis.
So 3 raised to the power of 2 is equal to 9, where both the exponent and the base are the same. 3 raised to the power of 3 is equal to 81. However, let's move on to the next hyperoperation. So 3 raised to the power of 3 raised to the power of 3, where all the exponents and the base are 3's. That results in 721 raised to the power of 1. Now we have reached a total of 92 words. If I continue further with 3.3.3 or other numerical values, we will notice that in these operations, the so-called prime numbers actually remain a minority. So, the question arises, why would prime numbers in multiplication be significant? This is an intriguing aspect to explore, as understanding the significance of prime numbers in multiplication can provide valuable insights into the underlying patterns and properties of mathematical operations.